Hello, everyone. Thanks for coming to NSF workshop on software hardware co-design for quantum computing. And first, I want to give a brief introduction to our steering committee members for the workshop. So our committee members comes from a diverse set of backgrounds and positions. Almost half of us have background in physics and half ours have background in computer science or computer engineering. Meanwhile, half ours comes from industry and half ours from academia. I think this also somehow like resembles the current status of quantum computing field, and full of opportunities and full of mixture. And first, a little bit of myself. I'm Yufei Ding. I'm assistant professor at UCSB. I got my bachelor and master degree in physics and PhD in computer science. So I'm already like kind of half and half. My research area is mainly about quantum compiler and quantum architecture design. And Kim Brown is a professor at Duke University. Kim has a track record in development of programmable ion trap quantum computer and co-designing both the software and hardware with trapped ions. He's also a leading researcher in the control of quantum systems for both understanding the neutral world and developing new technologies. Robert Weil is a professor at Technical University of Munich, Germany. Robert is one of the key pioneers for studying the design automation for quantum computers from multiple perspectives, including efficient quantum circuit representation, high-performance simulator, circuit optimization, and verification. So Ali Javadi is a principal research staff member with IBM Research. He leads the IBM's quantum software and compiler efforts. He also contributes to many optimization in the Qiskit compiler, as well as quantum computer architecture design at IBM. So if you are like playing with IBM software, then you know like Qiskit. Andrew Cross is the manager of the series of quantum computing and information group at IBM Research. Andrew is an expert in quantum error correction and fault-tolerant architectures for quantum computers. Andrew has been recognized widely for his contribution to the development of IBM Q experience and for authoring like earlier versions of the Qiskit open source software for quantum computing. And Gerard McLean is a staff research scientist at Google Quantum Artificial Intelligence Lab. Gerard is a world-leading expert in quantum chemistry. He pioneered many frontiers of quantum chemistry and quantum optimizations. He is also the main inventor of the variational quantum algorithm. So if you are studying quantum machine learning, you must know him. And Yu Shi currently leads the efforts of quantum compiler design at Amazon Braket. He also specialized in quantum architecture design, low-level device control, and form verification. And Amadina Kovano is our NSF representative. She is also the program director in the Division of Computing and Communication Foundations at NSF, National Science Foundation. So one of the key reasons the steering committee come together is because like we really want to push the high interest in quantum computing to some convergent efforts for future quantum computing design. And before that, I still want to give a short introduction to the quantum computing today. And especially many countries has announced their quantum strategies along with a large amount of investment. And here in the figure, I give a partial summary of the quantum hardware development in terms of both the number of qubits in the hardware and also like the time. It seems that like such worldwide push to lead to a significant progress in recent years. And you will notice that for a long time, say from 1998 to 2015, there's only hardware with a few qubits that can be accessed in the lab. But now we can have cloud accessible quantum hardware with hundreds of qubits. And it is also envisioned that in the next few years, we could increase the number of like qubits to 1 minute. So there's a big lift for quantum computing. And especially since 2015, there is a big wave for improving quantum supremacy on NISQ quantum devices. And those those devices only comes with dozens to hundreds of qubits without quantum error correction. And I think there's a big success in this period of time. And this success can be viewed as a good collaboration between physicists and theoretical computer scientists. And especially if you look at those quantum advantage experiments, physics had successfully demonstrate the computational advantage of quantum computing, and examples including Google, USTC, and Xanadu. And especially like theoretical computer scientists also devote heavily to this new wave. Especially they rely on their computation complexity theory to design those kind of circuits that are difficult to simulate classically. Yeah, so that physics does not really need to worry about some practical applications. But I have to say that the current status for quantum computing is that even though we have shown that it has some great potential, but we are not yet for those practical applications. So our workshop is set up to accommodate the new wave of quantum computing in the next like 10 to 20 years, and which we believe could be designing the better quantum devices for better experimentally proving practical speed up. And especially here, like better, we could means like larger, a larger number of qubits and better contributivity, like better gate fidelity, and also like better programmability. And we believe that this kind of progress will require a deeper collaboration between the physicists and general computer scientists, and also between industry and academia. And especially like there are some, I know that there are some concerns about why, or maybe like, could quantum computing survive or like really lead to this kind of practical speed up? I want to use one example in classical computing to convey my my opinion on that. And especially if you look at the general computing, the first general computing devices in the 1950s, and to like the machines we have nowadays, you cannot really believe, like if you like go back in time about 70 years, for 70 years, you cannot really believe we can have this kind of really powerful devices at home. You can imagine that, well, even nowadays, like the cell phone has a computation capability of the super computing devices of 70 years ago. And we have building much more complex and powerful computer today. And we could place over billions of transistors on one chip and achieve everything we can have. To this end, I think quantum computing, as long as there's no fundamental challenging, even there's a lot of engineering challenges, we should just go for it. And even though, like I said, we should go for it, I think we still want to find the best way to go forward. And especially like if you look at classical computing, we want to learn some experience and maybe reduce the time from 70 years to 20 years or 30 years, or maybe like even doesn't within 20 years. And especially if you look at classical computing, software and hardware and their co-optimization has been the key drive or the major drive behind the huge changes. And we believe like for quantum computing, we could also, this kind of software hardware co-design could also enable transformative scientific and industry progress. And as a computer scientist, I think just like all the other computer scientists, we are eager to work with physicists to figure out what are the key challenges and work together. And here, like the final page is about our final goal with this kind of workshop. And I think we hope it will not be only be a workshop. We really want to get some really convergent efforts towards the future of quantum computing. And before the workshop, we already finalized a set of topics we want to discuss today. And during the workshop, I hope all the panelists and the speakers could share like your concerns about quantum computing and your view views about the most important questions like to address in the next 5 to 10 years. And for our audience, I think it's time, especially those new to quantum computing field, I think it's time to take note, as you will get a lot of good questions to work on. And after the workshop, I think we'll have generate a final report that captures the key ideas discussed in this workshop. And even like you are not an organizer or like a panelist or speaker of this workshop, for general audience, if you are interested, you can also send me, like drop me an email about your thoughts about the future. And if your ideas is taken into our report, you can also be a co-author. So I guess that's all for my part.